Now we're going to start talking about our solar system. The solar system is the sun and everything that orbits around it. Often when we're talking about solar system and what it means, I have people who begin listing all of the things in the solar system, which is going to take a long time. Instead, we're going to use a more inclusive definition, which is the sun and everything that orbits around it. So this does include things like planets, moons, and asteroids and comets, but it's also going to include everything else. Any good model that's going to tell us about the formation of the solar system has to account for four properties. First, we have to worry about the patterns of motions of the large bodies. So in other words, why is it that the planets are moving the way they do, and also moons around those planets? Second, we have to worry about why we have two types of planets. We'll get more into it in a little bit, but there are terrestrial and Jovian planets. Third, we have to be able to explain where asteroids and comets come from. We see that they're all throughout the solar system, so how did they get there? And then fourth, we need to be able to explain any exceptions to the general patterns, particularly the patterns of motions. Okay, so we need to be able to make room for some exceptions. Alright, so let's look at some of these things that we're trying to explain. As we look at the motion of the planets in our solar system, we see that all of them orbit close to the plane of the ecliptic. The plane of the ecliptic is the plane that the Earth is orbiting on. So down here in this diagram, if you take a look, the Earth and all of the planets actually make a nearly flat disk around the Sun. There is a little bit of inclination. The planets are not perfectly in the same plane, but they are pretty close. Second, all of the planets have orbits with eccentricities near zero. If you remember way back, an eccentricity near zero means that it's almost a perfect circle. So it's not a perfect circle, but it's close to being a perfect circle. And that's what you can see here. This actually has the shapes of all of the planets' orbits, and notice they're all almost perfectly circular. Something else that we find is that all of the planets orbit in the same direction. If you're looking down on top of the Sun, then all of the planets orbit counterclockwise. That is, all of them are orbiting counterclockwise. And then last, most planets rotate in the same direction they orbit. So if you're again looking down on top of the solar system, most planets are orbiting counterclockwise. They're also rotating counterclockwise. Now there are two exceptions to this, which we'll talk about later. As we look at the planets, we can separate them into two groups. There are 4 planets that are close to the Sun. These are often referred to as the inner planets. And then there are 4 planets that are far from the Sun. These are often referred to as the outer planets. Now, although we can group them based on distance, we can also group them on properties. Okay, so the 4 inner planets are also known as the terrestrial planets. Terrestrial means Earth-like. So these planets are Earth-like. Now that does not mean that we could go and live there without any problem. The Earth is the only planet we can live on without any problem. But what we mean by it is that these planets have similar compositions to the Earth. All of them have solid surfaces and relatively high densities. So in this graph down here at the bottom, we're looking at the average density. Mercury is an average density of 5,430. Venus is at 5,243. The Earth has the highest density of 5,515, and then Mars has the lowest of the terrestrial planets at 3,934. But all of these relatively high densities mean that they have to be made of rock and metal. So they are terrestrial in that they're made of the same things as the Earth. The outer planets are also known as Jovian. Jovian means Jupiter-like. So we have the terrestrial planets, the ones that are Earth-like, and then we've got the Jovian planets, the ones that are Jupiter-like. These are the large planets in the solar system. They have both large diameters as well as large masses. Their diameters range from 5 to 11 times the diameter of the Earth. Now, although these are big, both in radius and in mass, they actually have very low densities. So again, this bottom line is the density. Now, on the scale that we're using, water has a density of 1,000. So that might help give you a little bit of scale. So Jupiter has a mass of 1,326. Saturn is at 687. Uranus is at 1,318. and Neptune is 1,638. Notice that Saturn is actually less dense than water. So, because of all of these very low densities, they cannot be made of rock and metal like the terrestrial planets. So, because of that, they have to be made of very light elements, particularly hydrogen and helium. So, because these are mostly hydrogen and helium are gases under normal conditions on the Earth, we sometimes also refer to these planets as the gas giants. Now, as we look throughout the solar system, there aren't just planets, we also have much smaller objects throughout. We can split them into two categories, comets and asteroids. An asteroid is a small and rocky object in the solar system. The highest concentration of asteroids is in the asteroid belt, located between Mars and Jupiter. Comets are small and icy objects. What we mean by ice in this case is not just frozen water, but anything that under normal conditions on Earth would be a solid or a liquid. If it is so cold that it has frozen, then we consider it an ice. So although they do contain water ice, we can also find things like methane ice or ammonia ice in these objects. The highest concentration of asteroids is located in the Kuiper belt, which is beyond the orbit of Neptune, and we expect another population of comets in a region referred to as the Oort cloud, which is way out at the very, very edge of the solar system. The last thing we need to be able to explain are some exceptions to general rules. We mentioned previously that not all of the planets rotate in the same direction that they orbit. The two exceptions are Venus and Uranus. Venus has a retrograde rotation. So if you remember way back, retrograde means backwards. So it's spinning backwards from the way that we would expect. Another surprising one is Uranus. Uranus is actually tipped over on its side. Okay, so most planets are more up and down as they're orbiting the sun. Uranus is actually tipped over, so it rotates on its side as it's going around the sun. What this means is that during a solstice, the sun is almost directly on the pole, shining down onto the pole, which is absolutely crazy. One thing that we've noticed with moons is generally moons orbit in the same direction that the planet is rotating, but that is not all. Some moons have a retrograde rotation, which we're going to have to be able to explain. And the last exception is actually the Earth's moon. The moon is surprisingly large compared to the planet that it's orbiting. In fact, most other terrestrial planets either have no moons. Mercury and Venus have no moons at all. Mars has 2 moons, although they're very, very small. They're not even large enough to be rounded by their own gravity. So the fact that the Earth has such a large moon is kind of surprising. We're going to need to be able to explain how that happened.